As we have observed in this example, and as we stated before, now we prove that all principal divisors are indeed degree 0 divisors. More precisely, we will see that for a non-constant function, if we denote its 0 and pole divisors, x0 and x infinity respectively, then indeed we will see that they have the same degree, which is equal to the extension degree of f over the rational function field k of x with respect to this transcendental. And in order to prove that, let me fix some notations. For the extension degree, we denote this non-negative integer by n. And let me denote the pole divisor of x by b. Here pi denotes the poles of the given function x. Then, indeed, by proposition, (1.3.3), we know this extension degree is bounded above by n. And if we are able to show that indeed n is also less than or equal to degree b, then we will get the desired for the pole divisor of x. And in order to prove this inequality, first let me choose a basis. And let me denote them by u1 up to un of the function field f over the rational function field k of x. And it is also possible to choose a positive divisor c, such that the principal divisors of the functions ui's is always bigger than or equal to minus c for each I. And for any natural number s, let me consider the Riemann-Roch space of the divisor sp plus c. And first, we can observe that the functions which can be written as a product of the x to the I times uj's when I runs through from 0 and s and j from 1 to n, we can see that these functions indeed lies in this L space, because their principal divisors can be written as I times the principal divisor of x plus uj, and If we write the principal divisor as the difference of the 0 and the pole divisor of x, first, we can see that this component indeed is bigger than or equal to minus I times the pole divisor of x, and by the assumption we know that this principal divisors is bounded below minus c, and if we consider this notation, and if we consider the inequality between I and S, we can see that this functions lies in the S space of the divisor SP plus C. Moreover, for each I and J, these functions are linearly independent over K, because otherwise, if do they have a non-trivial linear combinations with coefficients from K, not all 0, then we get a non-trivial linear combination of uj with coefficients from k of x, but this gives us contradiction by our assumption because we choose these ui's as linearly independent over k of x. So that means this contradicts to being uj's a basis. And thanks to this two observation, we can conclude that the dimension of this S space is bigger than S plus 1 times n, because we were able to find these many quantity linearly independent functions in this A space. Hence, the dimension of the divisor SP plus C is bounded below S plus 1 times n. And on the other hand, since pole divisor is a positive divisor and we consider the S as a natural number, positive natural number, and since we have chosen this divisor C as a positive divisor, that means the divisor SP plus C is a positive divisor. So in this case, this A space contains 0, and by proposition 1.4.9, we know that its dimension bounded above the difference of their degrees. So in this case, the 0 divisor has degree 0. And moreover, we can see that the dimension of the degree SP plus B is bounded above its degree plus 1 because of the dimension of the quotient spaces and the dimension of the L of 0. And so thanks to this lower and upper bound for the dimension of the divisor SP plus C, by comparing this to inequalities, and rearranging them depending on this, we see that the left-hand side in this inequality is independent of the choice of S. So in order to get this inequality for all S, it is actually this equality holds only when this quantity is positive. So this forces degree is bigger than or equal to n. Hence, the degree of the pole divisor is equal to the extension degree. And conclude to similar equality for the degree of the zero divisor. First, let me observe that the zero divisor of x is indeed the pole divisor of its inverse. So in this case, degree of the zero divisor can be determined by the extension degree of f over kx inverse. Indeed, which is equal to. And as a conclusion, degree of the principal divisor is equal to 0. And thanks to this theorem, first we can conclude that for two equivalent divisors A and A prime, they have not only have the same dimension, but also they have the same degree. And so in the previous lecture, we see that we observed that if we have a negative divisor, its X space is a trivial space. Now, in a stronger version, we will see that if a divisor has degree less than or equal to 0, then its dimension is equal to 0. And we can also characterize when a degree 0 divisor is also principal divisors by checking these three equivalent statements. Then the followings are equivalent. And in order to prove the statement A, if we apply the definition of the equivalence divisor, so that means if we write the divisor A prime is A plus the principal divisor of X with some non-zero X, its degree will be the degree, sum of the degree of A and the principal divisor X. And by theorem 1.4.11, we know that the all principal divisors are degree 0, so we get the equality. And we prove the statement B by contradiction. So let me suppose that a degree has a divisor has negative degree and its A space is of dimension bigger than 1. So towards a contradiction, let me suppose that degree A is less than 0 and L of A is of dimension at least 1. Then by remark 1.4.5 from Stitte note, we know the existence of the positive divisor, which is equivalent to A. And from part A, we know that for the equivalent divisors, we have the same degree. But this gives us contradiction because we suppose that degree A is negative, but for the positive divisor, it should have positive degree because its components will be positive and the degree of the places cannot be negative. This gives us contradiction. Hence, its L space is of dimension 0. And in part C, we consider degree 0 divisor. And we want to prove that if this divisor is principal, then its dimension is bigger than or equal to 1. So if A is a principal divisor with some non-zero function x, then we can observe that actually its inverse lies in the A space because the principal divisor of x inverse is equal to minus of the principal divisor x. And thanks to this inequality, we see that indeed x inverse in L of A by the definition of the A space. And since this Riemann space contains a non-zero function, its dimension is at least 1. And to see that degree 0 divisors A with dimension at least 1 indeed has dimension 1. And to see that by applying the remark 1.4.5 from the Stitte note, I think in the previous video I didn't put this enumeration. This is why I'm mentioning it again. We know the existence of the positive divisor A prime, which is equivalent to A. And from the statement part A, for the equivalent divisors, we know that they have the same degree. And by the assumption, this is 0. And if a divisor A prime, which is positive and it has degree 0, this is only possible if it is a 0 divisor. Otherwise, since the degree of the places are always positive integers, we will get a positive degree. And since these two equivalent divisors also have the same dimension, and the dimension of the L space of the zero divisor is 1, we can get the desired. And finally, excuse me, we will see that for the degree zero divisor, if a degree zero divisor is of dimension 1, so by this assumption, we can choose another function in the A space, and by the definition of the A space, the sum of the divisor A and the principal divisor Z is positive, and degree of A plus Z is equal to the degree A because of the degree of the principal divisor is 0, and by the assumption, we also suppose that this is of degree 0. Again, like in the same argument we use here, this divisor is positive and it has degree 0, so this shows us A plus Z in the zero divisor. So in this case, A is equal to minus principal divisor S, Z, which is equal to the principal divisor Z inverse. And we see that A is the principal divisor. So I think it's worth to mention that, so we see that the principal divisors has degree 0, but not all degree zero divisors are supposed to be principal. And we will point out the special cases when we consider the elliptic function fields.